Okay, welcome back. So the second type of second fundamental theorem of calculus problem you'll see will look like this. You'll be given a graph that's usually a piecewise function of some kind, and then you'll be asked some questions about it. So before we dig into this problem, I just want to go through and highlight a couple things to make sure that we're clear about before we start working. So in this problem, a lot of this problem is revolving around this function g of x, which is not pictured on the page. In fact, what's pictured on the page here is this function f of t. So this function is f. So when we start digging into the problem, we're going to need to separate in our minds the function that we have a picture of here, the piecewise function f, and then this other function g of t, which is an antiderivative that is not on the screen here. Okay, so I think the next few slides break up the problem so that we have some space on the slide to work. But part A is pretty simple, and it's where we're going to end up using the second fundamental theorem of calculus. So part A just says find g of negative 3, find g prime, and then find g prime of negative 3. So the equation for g of x is given right here. So if I want to find g of negative 3, just do this. Just plug in negative 3 for x, 0 to negative 3. Of t. Okay, so 2 times negative 3 is negative 6. To figure out this portion over here, the integral, I'm going to look over here at the graph of f, and the integral from 0 to negative 3, so from here to here, we want to find the area under the curve. That is what the integral from 0 to negative 3 is of f. And we're told in the problem that this is a semicircle. It's got a radius of 1, 2, 3. And it's only a quarter of a circle. So we want to find the area of a circle with radius 3 and then take a quarter of that. So this piece is 1/4 times pi r squared. Here r is 3. So we're going to get that this is 9 pi over 4. So the area underneath that semicircle is 9 pi over 4. Because we integrated from right to left instead of left to right, this is going to be a negative sign. All right. Okay. So then to get the final answer, g of negative 3 is just negative 6 minus 9 pi over 4. Okay, so then let's find g prime. So to find g prime, we just need to take the derivative of g of x. So I'll do that over here. So when I am going to take the derivative of g prime, the derivative of 2x is just 2. So g prime of x equals 2. And then now here's where we're going to use the second fundamental theorem of calculus. We need to take the derivative of an integral. So the derivative of the integral from 0 to x of f of t dt. We just covered that in order to do this, you plug in the bounds of integration. And so this would be just f of x. So it's a pretty simple one. The bound of integration is just x. So when you take the derivative of that, you just get 1. So the derivative of g is just 2 plus f of x. Pretty straightforward. Then we want to find g prime of negative 3. So then we just plug in negative 3. So now the only mystery is to figure out f of negative 3. So I'm going to go to my graph. When I plug in 3 into f, I get 0. So g prime of negative 3 equals 2 plus 0, which is just 2. So there we go. Part A is done. Let's take a look at part B. So determine the x-coordinate at the point at which g, so remember g is this antiderivative function, has an absolute maximum on the interval from -4 to 3. Okay, so this is a closed interval problem. And like any problem where we are looking for a minimum or maximum, the way we're going to do that is to take the derivative and set it equal to 0 and see if we can find a turning point. So we are looking for a turning point on g, which means that we want to find the derivative of g and set it equal to 0. But we just found g prime in the previous part. So g prime, again, was 2 plus f of x. So remember here, g prime of x is equal to 2 plus f of x. So if we are looking for a turning point, we are looking for places where g prime is equal to 0. So we're going to set g prime equal to 0. So we are looking for places where f of x is equal to -2. So I've got my graph of f over here. And so I am looking for places where the y value of f of x is -2. It looks like it happens right here. It looks like it's like 2.5, so 5 halves. And so we need to verify at this point, so we are looking for a maximum. We need to make sure that, so at a maximum, the derivative of a function needs to change from positive to negative. So if g prime is 2 plus f of x, we want to imagine a little sign chart for g prime. Our critical value is 5 halves. If we plug in a value to the left of 5 halves, so let's say our test value is just 2. When we plug in 2 into g prime, you get 2 plus, and then f of 2 is, looks like maybe it's about -1. But you're going to get a positive number here. And if we plug in a test value of like 3, so f of 3 is -3, so you can get 2 plus -3. That's going to be a negative number. So in fact, g prime is changing from positive to negative, and 5 halves is a maximum. So that's that. Part C, the last part, asks us to find points of inflection on g. So that's cool. If we want to find a point of inflection for g, we need to take the second derivative. But remember, whoops, we still have that g prime of x is equal to 2 plus f of x. So if we want to look for a point of inflection, we're going to take the derivative of g prime to get the second derivative. The derivative of 2 is just 0, and so you get that g double prime of x is equal to f prime of x. So we are looking for places where, g double prime is 0. That's where points of inflection are, where the second derivative equals 0. So that means we're looking for places where f prime is equal to 0. So when I look at the graph of f over here, if we are looking for places where f prime is equal to 0, we'd be looking for places, we would be looking for turning points on f. So if we're looking for places where f prime is 0, that means we're looking for turning points on f. So if you think back to graphical analysis we did, turning points on the first derivative correspond to points of inflection on the original function. So we have f here. We're looking for turning points. the only turning point that we have here happens at x equals 0. F prime, so f, the derivative of, so f is essentially the derivative of g, and then f prime is the second derivative of g. So we're looking for a turning point here where f is going from increasing to decreasing, and that only happens at x equals 0. So at f equals 0, at x equals 0, g prime of x, which is f, changes from increasing to decreasing. So g of x, the original function, has a point of inflection at x equals 0. Okay. So that's pretty much it. The part where we actually used the second fundamental theorem of calculus was in taking the derivative of this equation. So this part right here, where we found g prime and had to take the derivative of an integral. But here's an example for you all to try. I'm going to go ahead and leave it up here. Go ahead and try part A, and then we'll put up the solution for that. Okay, here's the solution to part A. G of 0, you just plug in 0 for x, and you get that you are looking for the integral from -3 to 0 of f of t. So you go to the graph of f of t here. That's the area under the function from -3 to 0, which is a trapezoid. It has a left base of 2 and a right base of 1. So just use the formula for the area of the trapezoid and got that g of 0 is 9/2. When we take the derivative of this integral, it's a pretty simple case. The upper bound is just x, so g prime of x is equal to f of x. So to get g prime of 0, I find f of 0, and that's 1. I read that off the graph right here. Okay, so take a second and try part B. Okay, here's the answer to part B. So part B asks us to find a maximum turning point on G. So if we're looking for a turning point on G, that is going to show up as an x-intercept on G prime. And specifically an x-intercept where we're changing from positive to negative. So maximum, the rate of change is going from a positive to a negative. Since we know from part A that g prime is the same thing as f of x, we can just look at our graph up here of f of x and find a place where there is an x-intercept where the derivative is going from positive to negative. That happens right here at x equals 3. And that's the only place that has an x-intercept where f is changing from positive to negative. So that's the only answer. Okay, take a swing at part C. Okay, so part C is a closed interval problem. So we're looking for an absolute minimum on a closed interval. So we want to find places where the derivative of g is equal to 0. That'll be a turning point, so that would be a candidate minimum. But then because it's a closed interval problem, we also need to check the endpoints of the interval to see if the function g actually takes on a minimum value at those endpoints. So our candidate locations for the absolute minimum are at x equals -4, because that's a turning point on the derivative, at x-intercept on the derivative, which means a turning point on g that is changing from negative to positive. So that is a candidate place for an absolute minimum. And then the two endpoints in the interval, x equals -5 and x equals 4. So over here in blue, I went ahead and checked the value of g at each of those three places. So g of -4, you get the integral from -3 to -4 of f of t, so the area underneath this graph f. from -3 to 4, it's the blue triangle. Because we're integrating from right to left, it's going to be negative, so we get -1. When I did g of -5, the area underneath